This is part 2 of the video lecture for Math 181 for Monday, April 27th. And the topic is using integrals to calculate the volume of solid objects. The first example we'll do is calculating the volume of a sphere, okay? Now actually we already know the volume of a sphere, but we're going to use an integral to calculate this. And what we can do to solve this problem is I'm going to create a coordinate axis system, x and y. And then I'm going to place a sphere on this coordinate axis system. A sphere which is centered at the origin. Okay. And now the trick with volumes is these are three-dimensional shapes. So it's hard on a two-dimensional whiteboard to represent a three-dimensional shape. But imagine this sphere is not just a circle, it's a three-dimensional object that's centered on the origin. So it's coming out of the board as well. Okay. And we can write here the radius of this sphere. The radius is r. Okay, and this goes up, we'll imagine this goes up to a point here along the surface of the sphere. And we're going to drop down a perpendicular here. So this length here is x, and that length is y. Okay, and this is our radius of the sphere. And we want to calculate the volume of this sphere. Okay, we're going to use this volume equation. So the basic idea is we're going to take this sphere and we're going to cut it up into a series of very thin slices. And so this would be, let me draw this in a different color. Again, it's hard to depict three-dimensional shapes on a whiteboard, but we're going to divide the sphere into slices that look like this, that have a certain thickness like that. So we have, these are actually discs is what they are. Okay, and the thickness here, the thickness of our disk, okay. So now let's just zoom in on this disk. We have a disk that looks like this. And I'm not a great artist, as you guys will see. But this is our disk. It has a thickness of dx, okay. And this disk has a radius. What is the radius of this disk? Well, that's different than the radius of the sphere. The radius of this disk is equal to the height here, right, is equal to y. So the radius of this disk is y. Okay, what is the area of this disk, of the cross-sectional area? What is the area of the face of this disk? Well, the area is simply pi r squared, right? Pi r squared, and in this case, the radius is y. So the area of the face of this disk is pi y squared, and the thickness is dx, okay? For a circle, we know that the equation of a circle is given by x squared plus y squared equals r squared. This is simply the equation of a circle. So we know how x, y, and r relate. Now if we solve this for y squared, we get y squared equals r squared minus x squared. Okay, so I'm going to plug this into my equation for the area of each of these disks. The area is pi times r squared minus x squared. That's the area of each one of these slices of my sphere. Remember, we're dividing this into a whole bunch of slices. The area of each one of those slices is pi times r squared minus x squared. The thickness is dx. And now we can calculate the volume of our entire sphere, okay, by using an integral. So the volume will be the integral with certain limits of our area function, which is pi r squared minus x squared. And then we're going to multiply this by dx. Now what are the limits of integration here? Well, this point right here is equal to r comma 0. This point over here is minus r comma 0, right? The sphere extends plus or minus r along the x-axis. So our limits of integration are minus r to r. Now there's a clever trick we can use here. Let me go over here. This volume, this is a symmetric function. So we don't need to integrate from here all the way to here. We can simply cut this sphere in half, integrate from here to here, and then multiply by 2 at the end. And that'll give us the same volume. So this integral is actually equal to 2 times the integral from 0 to r of pi times r squared minus x squared dx. Okay. That's a clever simplification. The more you do calculus, the more use you get to doing it. Why do we do that? Because it's a hassle. I'd rather plug in 0 as a limit than minus r, so this integral is easier to evaluate. That's why I did this. Okay, let's go further here. Now we can pull out the pi. We get 2 pi times the integral from 0 to r of r squared minus x squared dx. Okay, now we can evaluate this integral. This is equal to 2 pi. Now here r is a constant, so we can, the first part of this integral, we can pull the r squared out, and the integral of dx is just x, so we get r squared x for the first part of this integral. In the second part, we have the integral of x squared dx, and that turns into x cubed over 3. So this is now the evaluation of our integral, right? Again, r squared is a constant, and this is evaluated from 0 to r. So I'm going to plug in these integration limits, and now I get 2 pi times r squared times r minus r cubed over 3. And let's simplify this. This is 2 pi times r cubed minus r cubed over 3. Okay, well this is simply equal to 2 pi times 2r cubed over 3, which is equal to 4 pi r cubed over 3. And that is the volume of this sphere. Well, guess what? That's the equation for the volume of the sphere with the radius r. So we already knew this, but this is kind of cool. We used calculus. We used this idea of dividing our volume into a series of slabs and then summing them up. In other words, doing an integral, and we get this. We confirm this equation for the volume of the sphere. Okay, let me do another example problem with you guys. Okay, in the second example problem, we're going to calculate a solid of rotation. I'll explain what that means. So we want to calculate the volume of the solid. The volume of the solid obtained by rotating the line y equals x about the x-axis from x equals 0 to x equals 1. We're going to find the volume of the solid obtained by rotating the line y equals x about the x-axis from x equals 0 to x equals 1. Okay, what does this mean? Well, let's draw a graph. Let's draw the line y equals x. Okay, this is our line, y equals x. Okay, and what we're going to do is we're going to imagine we took this line and we rotated it around the x-axis. Okay, we rotate it around the x-axis. That will generate a solid. And what this will, I'll do my best to portray what this looks like. Again, it's difficult when you have a two-dimensional whiteboard to represent a three-dimensional object. But basically, you'll basically get a cone-shaped object. Okay, and this is how it will look. Like that. You'll get a cone-shaped object that's solid throughout. Okay, by rotating y equals x about the x-axis. How do we calculate the volume of this cone-shaped object? Okay, that's the question before us. Well, we're going to use that same volume integral we had. So what we're going to do is divide this region into slabs. So let's imagine this is one slab we have here, and this slab has a thickness of dx. Okay, what is the height of this slab? This height is, the height of the slab is actually, well, in this case it's a rectangle, not a slab yet. The height of the slab is equal to x, right? The height, because this line is y equals x, the height of the slab is x, and now we're going to rotate this around the x-axis. So this will create a disk like this, a disk shape. That'll create a disk shape like this, right? So here's our disk. Let's draw our disk in detail. Okay, this is our disk. It has a thickness of dx. Okay. we know this, so this dimension right here, our radius of our disk is simply equal to x. Okay, that means the area of our disk is going to be pi times the radius squared, so pi x squared. That's our area, right? And this is now our thickness, so we can use our volume integral. Our volume integral will be the integral from 0 to 1, because we're only going from x equals 0 to x equals 1. That's the only part of the solid object we're considering, times the area function, which is pi x squared. And we're integrating this over dx. So this is what we get. And now I can pull out the pi, and we have an integral from 0 to 1 of x squared dx. And if we integrate that, we get pi times x cubed over 3, evaluated from 0 to 1. Okay, and this equals pi over 3. Okay, so that's pretty simple. The volume of this conically shaped solid object, by rotating the line y equals x about the x-axis, is pi over 3. Okay, in part 3, I'm going to do 2 more examples.